go. Yep. So we got 2 people showing up early. Nice. All right. How are you guys? I hope you guys are starting to work on the program. I know one person, at least 1 or 2 people, are done with it already. All right, excellent. So I think most people can guess what today's topic is going to be. Oh, okay. Well, that's not a bad thing. I mean, it needs to be done anyway, right? I mean, so now you have the whole weekend. Well, I shouldn't say the whole weekend, but now you don't have to worry about the negative exponent. We just have the positive exponent assignment to work on. So that's it's not a waste of resources. So well, floating point addition is going to be a little bit hairy. It's going to be because you have to align the decimal point. So you just have to shift a whole bunch of stuff and then hope that there's still enough precision for adding purposes. So that's always a little bit tricky. Yeah, I have always recorded my lectures, even when I was face-to-face before the pandemic. So that's why YouTube has so many recording, because I have been recording my lectures, even when I was completely face-to-face for several. I cannot remember how many years, but it has been a while. Oh, okay, sure, yeah. You can even watch recordings from past semesters, even though the way I teach certain topics may change depending on depending on whether I have some realization. It's like, oh, okay, this may be a better way to explain the same concept. But you can actually just watch years of recording of a class, just kind of on and off. It's not the same thing as going to class because you cannot ask questions interactively, which I think that's the main reason why I want to do synchronous classes, even though it's 100% online. And we got about 1 minute to go. All right, let's see how many people on the live stream side. Oh, it doesn't show anyone over there. Oh, that's strange. The stream is on, I can see myself. It does show that there are 15 concurrent viewers. Okay, maybe that's it. All right. All right, I'm gonna close the live stream window, and now it's time to get started. All right. So what we're going to do today is really just a continuation of what we did on Tuesday. On Tuesday, we handled 5.2.1, and what we'll do today is to handle 5.2.2, when the exponent of 10 is more than 0. So more than 0 it seems to be easy to handle, at least for certain cases, and then it doesn't seem easy to handle after that. All right, so let me just go ahead and show you my note window over here. So we're going to consider this floating point number 1.23 times 10 to the power of 45. So the first iterations would be pretty easy to do, because what we can do is to say, okay, so what we have here as a value to represent is 1.23 times c dot 10 to the power of 45. This is what we start off with, and the program, without you doing anything, will automatically convert it to 123. But since we have two left shifts, with the coefficient, so that means I have to decrease the power of 10 by 2. So now we have 10 to the power of 43. So now we want to continue this trend here and continue to decrease the power of 10 until it is 0. So at first glance, this is pretty easy to do, because what I can do now is to keep multiplying the coefficient by 10, and then for each time I multiply the coefficient by 10, I can decrement the power of 10 or the exponent of 10 by 1. So at some point, okay, so if I keep doing this, just to do it maybe one more time, and 42, 40, goes down to 41. So this part seems easy, but it's going to stop at some point, right? And at some point, I can no longer multiply the mantissa or the coefficient by 10 anymore, because if I did, it's going to exceed what a 64-bit unsigned integer can represent. So that means, you're going to have a similar control structure like what we talked about on Tuesday, except in this case, you are trying to see if multiplying the coefficient by 10 again is going to exceed the largest integer that you can represent using 64 bits. So I'm just going to throw the equation here. So at some point, your coefficient, I'm just going to use the letter C to represent it, just like on Tuesday. So at some point, C times 10, or 10C, is going to be greater than the maximum integer that you can represent. So I'm going to use math rm max, and that would be the condition to stop. Okay, so you keep multiplying the coefficient by 10 until the condition that I have specified here is true. So then what do we do? It's like, okay, we have just filled up the coefficient and we can no longer multiply by 10 anymore. So I'm going to wait for you guys to answer the question. So what do we do, once we get to that point? So I think in this case, it is, so in this very specific case, 1, 2, 3, followed by, let's see here, we can have 19 digits including the 1. So 19 minus 3 is 16. So I have 16 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Alright, so at this point, if I multiply the coefficient by 10 again, it is going to exceed what we can represent using a 64-bit number. So what do we do? Let me make sure that I'm on the right text channel. I am on the right text channel. There we go. We got a few people typing, making some suggestions. Yep, we start to divide it by 2 in order to, quote unquote, make room for another multiplication by 10. All right, so let's go ahead and do just that. Okay. I'm debating in my own head, whether to illustrate this, using what we are seeing here, or whether to switch to a spreadsheet to actually do the calculation. I think I'm just going to switch to a spreadsheet, because that's just way more convenient than having to do all the math using a text editor. All right, so this is, let me just kind of go ahead and erase what we had earlier, and now we have 1.23E19. That's, if I multiply this one more time by 10, it's going to exceed what 2 to the power of 64, the whole thing minus 1, it's going to exceed that amount. Okay, so we want to divide it by 2. Alright, so we say, what about this number and divide it by 2? We look at this number. If we multiply by 10, it's still going to exceed 2 to the power of 64, the whole thing minus 1. So we're going to have to divide it by 2 again. So we say, okay, let's take this number and then divide it by 2. That's still too much. Okay, we need to divide it by 2 again. So we look at this number and then we divide it by 2. And then finally, we look at this number and go like, yeah, I think we can multiply this number by 10 and it won't exceed what we can represent using only 64 bits as an unsigned integer. Alright, so at this point, we are going to multiply it by 10, and then we're going to decrement the exponent of 10 by 1. But you might recall, every time we do a division, we are potentially losing precision, because we are using integer division, and we are not dealing with double or float in all of these calculations. So the question is, what trick do I need to use in order to make sure that even if I lose precision, at least I won't have a bias when I lose precision? So what are we going to do in order to make that happen? Add 1 before dividing. Very good. All right. So that means, in the notes, I'm just going to say, well, now we need to divide C by 2. And every time we divide it by 2, so I'm going to use a left arrow to represent assignment, because otherwise a single equal also as assignment versus comparison is not going to be very easy to, it's going to be confusing. So I'm going to use a left arrow to represent assignment. And this is going to be the floor, right? So L floor for the left hand side of a floor symbol. It's going to be a division, which is kind of a fraction. So it's C divided by 2, and then the right floor. But I just forgot one thing that I said earlier. Okay, one thing that Eric reminded me that we should do, which is to add 1/2 of the denominator to the numerator before the division, because we have already established that this is actually the same thing as rounding, except it does not involve using math.h, it does not involve the use of double, it does not involve the use of float. Everything is still being done using integer arithmetics. So that's how we need to do, that's what we need to do to divide C by 2. Now you might say, this add 1, this plus 1 to a huge quantity like this is insignificant. Well, in one single division, it may be insignificant, but if you keep doing this many times and you are forgetting the plus 1 here, or forgetting the plus 5, in the negative exponent algorithm, the result is going to be changed. It's going to be detectable. It's going to be significantly different compared to what it is supposed to be. So it is really important to remember to add 1/2 of the denominator before you divide it. So this way you are incorporating the mechanism of rounding, but only using integer math, which is kind of a, I think it's kind of a neat trick, to be able to do that. So are we doing okay so far? So we have to keep doing this until what? Until there's room, right? So what is the condition to stop dividing C by 2? The condition that we need to reach is when there's enough room, right? So we need to make sure that C is less than or equal to max divided by 10. Then we can go ahead and divide by, we can multiply C by 10 again at that point, because it's, even if we multiply by 10, it's going to be less than, and probably should not be a less than, equal to, should be just kind of, let's see, less than or equal to, or less than. There's also the plus 1 involved here, so it's going to be the same deal as last time. The plus 1 becomes a minus 1, so the minus 1 has to be done before the division, like so. And this is supposed to be less than or equal to LE. There we go. So that's the condition that you need to, that's the exit condition for dividing C by 2. Sorry, it's dividing it by 2. Keep dividing it by 2 until this condition is true. Then you can multiply C by 10 again, and and as a result decrement the exponent of 10 by 1, and you keep doing this until the exponent of 10 becomes 0. Alright, so that's about it. Okay, are there any questions about how to handle the case when we have a positive exponent? It's in many ways it's kind of the same way as what you're doing, what we have talked about on Tuesday, except we just kind of reverse the direction of a few steps. So do we have any questions? Because without any questions here, we are pretty much done with floating point number representation. Okay, doesn't seem like there are any questions. So what I'll do is I'm going to go back to my module. And this is the 5.2.2 is specific to handling a positive exponent of 10. All right, excellent. Okay, so we are just going to move on. So normalizing the mantissa is pretty easy to do because by the time you're done with the homework assignments, both of them, because I'm going to assign the positive exponent today, so you do have a little bit of overlap between the two, but it's not going to be that big of a deal because once you get one done, the other one is very similar in terms of what logic we're going to use, except we're just going to be flipping base 10 and base 2 because we are what you're dividing and what you're multiplying and which exponent you're adjusting is exactly kind of the opposite of the other one. But the principle, the idea is still the same. Alright, so once you're done with both of those homework assignments, you're going to end up with a mantissa that has 64-bit of significance. And as a result of that, you're going to have to do some normalization before you can actually use that coefficient. And then you're going to have to figure out the exponent. And then you're going to have to pack the entire thing back into a 64-bit number. So we'll talk about that after I take row today. Alright, so row taking for today. I cannot remember which word I have. Oh yeah. Okay, now I remember which word I. It's not exactly a word. It is actually an acronym. I would say it's probably more of an abbreviation rather than an acronym because I'm not really sure how to pronounce this. OER. I'm gonna put it into the text channel and so that you guys can copy and paste it once I release it. I have not released the row taking activity yet because I forgot to set the time for this. Alright, so let's just say that this is due at 6 p.m. Plenty of time to put it in, right? We got what? More than 15 minutes to do it. There we go. Alright, so some of you are probably thinking, what is it? What does it represent? OER, right? And having that question in your mind is actually a good thing. It's curiosity. And curiosity, trust me, in the profession of computer science or software engineering or programming, is really, really useful. I'll get back to why curiosity is important. But I'm going to explain what is OER. OER stands for Open Education Resource. In other words, free textbook, free media, free stuff, so that you don't need to buy textbooks. And I use OER as a word because I am now an OER mentor at ARC. So other professors who want to author their own content can now ask me about what tool I have used, what I think of certain tools, and what I think of Markdown, what I think of LaTeX, and so on and so forth. So so that's why that word, that abbreviation was in my mind today. Oh, the date is incorrect. Oh, right. Yeah, because it's not 0203, it's 0303. Okay, fine. I'm going to change the name. I mistyped it. So 0303. Thank you for noting the error. It is now corrected. No, I have not completed that yet. I will work on it. Yep, during the work week, it's just a lot of stuff happening, and uh, because I'm also department chair, and there are a few things I need to take care of also as department chair. But I'll get to it. You all get A plus. ARC doesn't care about the plus or the minus, so the best you can do is an A. There's no such thing as an A plus. Yeah, it is going to be it's going to be interesting. But I do this every semester. So what I do is I just I download all of your documents as a PDF, and then I load it onto my tablet. My laptop is actually a tablet too, but I used to have a black and white e-paper kind of tablet. But I found that it has its own limitations. So I might switch back just to use my computer tablet, to do the grading. But I really need to sit down, and I can probably grade 6 to 8 exams from question 1 to question 6, and then I need to take a break because I will put it this way: grading exams can be a little bit mind numbing, because I need to follow the logic of in the answer, because that's the idea of okay, can I give this person partial credit, because throughout all the steps, some of these steps is evidence to showing that person has some understanding of a specific key point that I'm looking for. So I cannot just look at the final answer and go like, yep, that is right, full credit, or no, it's wrong and 0 credit. I cannot do that. Because there are other times where I can look at the final answer, it's 100% right, but then when I look at the steps, okay, some of the steps do not make sense, okay, and in those cases, it's not going to be a full credit for sure. So I need to decide, also in those cases, how many points to give, to based on that specific answer. So it's a lot of evaluation, and evaluation or judging is one of the things that INTPs do not do very well. And I'm an INTP using the Myers-Briggs type indicator. So there we go. All right, but I can at least finish up the program, to give you the keys or the correct answers, and then I can give you access back to your own answers, like view only. So this way you can look at your own answer, you can look at the key, and at least what the answer is supposed to be. So that can help some people understand, approximately how they did in the exam. So I can certainly do that part. And the code is not difficult. I just have to sit down and finish up, writing that code, and so that the key can be published. OER peer mentor. So it's not for students, it's for other professors. I think I have at least one math professor who has expressed interest in authoring his own material for classes. So I'm the mentor for other professors. But if you guys have any questions about publishing stuff using math equations and whatnot, I'll be more than happy to share what I know. In the probably it's going to go into the off-topic text channel, because it's not exactly what this class is about. All right. So, but thank you for the reminder, because if you guys did not remind, I would have forgotten to finish that program to release the key. So thank you for the reminder. All right. Anyway, so we are pretty much done, because this last part here is just basically about shifting a whole bunch of bits, 12 bits to be exact, out of the 64-bit coefficient that your program is going to end up with. And then we just have to figure out, out of those, okay, how many we're going to have to get rid of the initial one, right? So so the rest become the fractional part. So I just misspoke. Okay, we're supposed to keep 53 bits, so we're supposed to right shift 11 times. But after we right shift 11 times, bit 52 is also useless because it is guaranteed to be a 1. So we don't need a bit, to be represented explicitly when we know it is going to be a 1. So we're going to reclaim that bit so that it would become a part of the exponent of 2. But then, the exponent that ends up in your program, in the member called E2 of the structure, that is the correct exponent, but it needs to be biased before we convert it into a 11 unsigned integer representation. So we're going to have to add the bias, which is 1023, and then we have that binary bit pattern. We shift it in, and then we finally have the sign bit, which is the most significant bit, or bit 63. We also, we can, that one we don't have to shift in. We can just kind of OR that into the bit pattern. And then we're done. Okay, so the rest of the conversion is a whole lot more just chores. Okay, it's not really that interesting. It doesn't involve a whole lot of control structure. So that's also partially why your program doesn't have to do the rest, because it does reflect that you understand where the bits are supposed to go and so on and so forth. But at the same time, it is also not exactly interesting either. But with that, we are now finished with the double precision floating point number topic. So if you guys don't have any questions, we're going to move on. We're going to move on to a entirely different topic. In fact, it's a different direction for this class. We're getting closer and closer to actually being able to write programs using assembly language. All right. Yes. So about debugging, okay? As I might have mentioned in this class, you may not have been taught how to debug a program in CISP360. So the first thing is use the right tool. So I'm going to talk just a little bit about debugging, and in this case using online GDB. Now I'm using online GDB as an example simply because anyone who has access to a browser can use it. So you can be using a Chromebook and still be able to use online GDB, and that's why it is helpful. So the first thing you need to do is to know how to set a breakpoint. So I'm going to talk about certain things that some of you will encounter, which is the problem of an infinite loop. Alright, so let me get back to the entry point somewhere right there. Okay, so I'm going to write myself an infinite loop. So I'm going to just say while Pn is greater than or equal to 0, do the following. Obviously this makes absolutely no sense in your homework assignments, so please do not copy this as a part of your program because it is guaranteed not to be useful. All right, and I got a few questions about what syntax to use when we need to refer to members of the structure the Pn is pointing to and stuff like that. That stuff is supposed to be taught in CISP360, but I understand sometimes the professor may run out of time and therefore not be able to introduce some of those concepts. So so if you have minor questions about the syntax of how to do this, I can answer some of those questions. The other way to do this is to use the pointer notation, a dash followed by a greater than symbol. And in this case, I'm going to say, let me think. Oh, let me make another syntactic mistake here. Not syntactic, but just bad coding here. Alright, so now we can, I'm going to change E10 and subtract 1 from it. Okay, there we go. So syntactically speaking, this program actually, it will compile. It makes absolutely no sense whatsoever, okay, except that it's guaranteed to get into an infinite loop. So let's go ahead and just kind of test run this program and just kind of watch it getting into an infinite loop. So we'll go through debug, And remember, when you run the program, it's R and then followed by dash and then followed by the base 10 scientific notation, which in this case I can just give you 1.23 e negative 45. Press the enter key, and the program is stuck in an infinite loop. What do we do? Okay, first thing, to break out of an infinite loop, you type Control C in the debugger. So you type Control C, and it's not exiting the program. All it is doing now is to pause the program, and it will tell you which line it's in. So that means if you are in an infinite loop, whatever line you're in right now, which is line 129, is a part of the loop. All right. So if you know this is a part of the loop, then you know at least the minimum range of that loop. This entire block here is a part of the infinite loop. So the next question here is, why are you in an infinite loop? What is causing this infinite loop? The simplest answer to that question is the condition of the loop is always true. So the next question is, what in this loop body is supposed to change that condition so that that condition will eventually be false? Okay, so that's the kind of thinking that you should go through in your mind when you have confirmed that you're in an infinite loop. But in a program like this, okay, with a debugger, you actually have a lot of tools to help you understand why you're still why you're in this loop. So what you can do is, the first thing you can do is to say, okay, tell me everything in Pn. So you look at this Pn here and you say, okay, the coefficient is awfully large, and so is the exponent of 10. But then you want to know, but what about the very condition that I'm using here to basically specify when the loop should exit, right? So you look at print Pn, and Pn is some pointer. I know it's really hard to read this value. I can just tell you it's a bunch of hexadecimal digits, but it is not 0, right? So what you're going to do is you can now single step. So there's a single step, and then you single step, and you single step, you single step. Now we have gone through at least one iteration, and then you look at your Pn as a pointer again, you go like, hey, that has not changed. In other words, I have gone through one entire iteration and Pn itself has not changed. So that, I mean, it's not a guarantee that it will never change in the loop, but it's a pretty good it's strong evidence supporting that there may not be any code in the loop itself to change the pointer itself, and as a result, it's always going to be non-zero, and if it's always going to be non-zero, then your loop will never exit. Now you're not going to get into this very specific type of logical error because your conditions are all based on values, right? But if you set up those conditions wrong, you can potentially still be stuck in the loop. So I'm only describing the logic or the rationale that you can utilize when your program is in an infinite loop, and also pointing out what you can do in the debugger so that you can say, okay, now that the program has paused its execution, let me take a look at what is in the structure that Pn is pointing to, because a lot of times that alone will give you some clues as to why your program is not working correctly. So just a little bit of debugging techniques. I know some of you are used to cout or printf. When your code is not working, you just kind of sprinkle those things around. It's not like that approach doesn't work. It does work. Okay, sometimes I use that approach too, but it's not the most effective way to debug a program, especially when you have a full-blown debugger like what we have here. With certain types of programming, you cannot have actually a debugger attached to the code that's running your program, so you don't have a choice. But in this case, you have a full-blown a debugger built into this entire interface. So my suggestion is learn how to use GDB, because the time that you invest in learning how to use GDB most likely will pay itself off because you can find a bug a lot faster than the other ways of debugging a program. And GDB is not just for this class. Okay, many of you will move on to a 4-year university where the environment of writing code is C++ or GCC, and then the GDB is going to be, guess what, the debugger. So learning how to use a debugger most likely is not going to be a waste of time. All right, so I think I have preached enough about why you should use a debugger. So without any further questions, I am going to move on to the next large section of stuff in Canvas. So let's go there. So the next main module is not assembly language programming yet, but it is called von Neumann Architecture and Memory. So this section here is a bridge. Okay, this entire collection of modules is a bridge between how we represent values, which is kind of the whole thing that we have talked about in from week 1 up to this point. This one is about the various things that we have in a computer, particularly how does a processor maintain data. Okay, how does it know that, oh, this thing had a value of 2 and adding 1 to it, now we have 3, and so on. So let me go back to, oh, I got a direct message, and let me see whether it's related to this class, because sometimes I get stuff that is not related. Okay, I'll deal with that later. All right, so getting back to the von Neumann architecture and memory. All right, so to get into this particular section here and to understand the significance of the von Neumann architecture, I'm going to show you some pictures of computers that did not have that were prior to von Neumann architecture. So I am going to use okay, I'm just going to go to Google. You cannot see the search words until I get here, so I'm going to show you what words I use to search for stuff. So we can use von Neumann. I was corrected several times about my pronunciation of this particular last name. I think it's an Austrian last name. And I think it's supposed to be von Neumann, not von Neumann. Oh, that's not what I want to look. I want to look up wire wrapped processor. Let's add messy to it. There we go. The first picture is exactly what I want to show. So in the good old days, all right, this is how we specify how a processor is supposed to work. Okay, because we are basically President's Day sale, and no, I'm not gonna subscribe to Wired. There we go. Okay, now we can get back to the picture. So this is a picture of a processor, and this particular technique of connecting contact points is called wire wrapping. And the reason why it's called wire wrapping is because you're literally wrapping the exposed portion of a wire around these posts. So each post is representing a contact point of a specific component, and you basically just wrap the exposed or the conductive part of a wire around the post, and then connect, and then do the same thing with the other end to another post of another component, and that's called wire wrapping. The website lives up to its name. Oh, that is funny. The pun was not intended. See how things just kind of works out sometimes? But that was very good observation, Gabrielle. Good observation. I like that. All right. So every time, okay, you want to change your program. Every time you want to change what you're computing, how it is computed, you're going to have to go back here, unwrap the wires, okay, and then rewrap the wires. And wire wrapping is not easy to undo because you end up with a stack, okay? Literally, you end up with a stack of these wires being wrapped. So if it is the bottom part that you need to unwrap, guess what? You have to unwrap all the top bunch of wires first. So now you have to unwrap a bunch of stuff that you actually may not need to unwrap just to get to the part that you have to unwrap, and then after changing that you have to wrap everything back onto that post. Oh yeah, this is way worse than punch card because punch cards were around after von Neumann's architecture. That is why. So that's a very good observation as well, Chris, because punch cards were way past what we are seeing here with wire wrapping. Okay, so just kind of get this in your mind. In order to specify how to compute, in other words, programming, you are physically wrapping or changing contact points or the connectivity of contact points inside a computer. That is how computers were programmed before the von Neumann architecture became the thing, to design computers. So now comes this guy. Okay, so I'm going to go back to Google again, and this time I'm going to look up von Neumann. Alright, so here's von Neumann, and the first link is to go to Wikipedia. So that's where we are going, just for a very short amount of time. So I was wrong. Okay, it's not Austrian, it is Hungarian. There we go. It is Hungarian. All right, so this is the guy, and the first thing some people may notice, okay, not that you guys, really care about this, was how long did he live, right? The guy was born in 1903, and he passed away in 1957, age 53. So he died fairly young, and the reason was most people speculate. Most people speculate that he got cancer, and that's how he died, from all the testing of the not nuclear bomb, not the fission bomb, but the fusion bomb, hydrogen bomb. Because he was also involved in the development of the hydrogen bomb, which is actually a misnomer because they are actually not using hydrogen. They were using, I think, lithium as the fuel of those specific devices. Anyway, yeah, radiation poisoning, exactly. So this guy was a genius, okay, and not in the sense of a genius in the sense of like Albert Einstein. Now Albert Einstein was a genius in terms of physics, right? Theoretical physics. He discovered relativity and so on and so forth. So he was famous for that one thing. This guy, on the other hand, was famous for a lot of things. So if you just kind of look into his contribution in the fields, he is mathematics, foundation of mathematics, functional analysis, ergodic theory, group theory. Group theory, by the way, is interesting, especially for those of you who want to get into cybersecurity, especially the cipher, the encryption side. Group theory can be the foundation of a lot of those particular theories. Representation theory, operator, algebra, geometry, topology, blah, blah, blah. But these are all math. Moving on to physics, right? Quantum mechanics, hydrodynamic, quantum statistical mechanics, economics, okay, and computing, and so on. I mean, the guy thought about self-replicating machines. I mean, he's way ahead of his time, right? I mean, he's way ahead of his time. So we are specifically looking at one of his inventions, which is the von Neumann architecture, okay, which is named after him. So you might ask, so what is the big deal? I mean, this guy, being a super genius, what was his contribution? So if I just tell you what it is, if I just kind of describe, what he quote unquote invented, you're gonna go like, so yeah, so what's the big deal? Well, it was a big deal because nobody thought of that, okay? Back in those times. Now we think of this as normal, usual, there's no big deal because we have been living in the era of computers for so long. So a lot of the inventions, back in those days, we really don't see the significance anymore because it's just normalized, at this point. Oh, okay, cool. I did not know that, Chris. All right, cool. All right, so getting back to his contribution. So his contribution was, so memory is nothing new, okay? Memory in the computer was nothing new because when you are computing, let's say, the trajectory of a projectile from a Navy ship, okay, which was one of the earliest application of computers, you kind of need to have variables, right? You need to maintain, because you're dealing with tracking the trajectory, so you need to remember its current position, its current velocity, blah 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 blah. So you do need variables and memory inside a computer in order to keep track of those amounts that are changing all the time, throughout the computation. So memory was nothing new, except it was only used to represent data, okay? The numbers, the values being processed. So what John von Neumann said was very simple. By our standard, it's like really simple. He basically said, why don't we also use memory to store instructions so that what the computer is going to do, the behavior of your computer, is now dependent on the content of memory instead of how the wires are being done. That was his contribution. Sounds pretty simple to us, but in his time, it was revolutionary because now you basically have one flexible architecture that basically has a mechanism to go to memory to grab or fetch an instruction, decode the instruction, then it knows what to do, and then after that step, it goes back to memory. Fetch the next instruction, decode it, figure out what that is supposed to do, and so on and so forth. So in order to change the behavior of a program, all you need to do now is to go change the locations of memory because that is still a lot of chore, okay, but not nearly as much as changing the wiring physically inside a computer. Changing the content is relatively simple compared to changing the wiring. Alright, so for those of you who are thinking, so how can changing memory locations be such a problem? Let me go through, let me find this kind of picture because then you guys will go like, wow. Okay, so I think it's called the Altair computer. Might have misspelled it, but Wikipedia or Google finds it. So this is the Altair computer, the Altair 8800 computer. So we're gonna zoom in. All right, so let's see if I can actually zoom into these toggles. All right, so this is relatively new because we see LEDs. So every time you see LEDs, it cannot be that old. So basically, you have a bank of switches. To specify which location you want to program, you flip some of these switches. So you have to convert the location to base 2, and then you have to use these switches to specify the location. And then you toggle one of these buttons here. I cannot remember which one, but you toggle one of these buttons so that it would basically say, okay, I'm now pointing to that location. Whatever you change now is applied to that location. And then you flip, a whole bunch of other switches to specify the new content at that location. And then you move on to the next location, do the same thing. So it is still a lot of work, but it is relatively simple compared to having to go in, unwrap a bunch of wires, and then rewire that bunch of wires and hope that in the process you didn't mess up something. So his contribution, the von Neumann architecture, was huge because without that concept, computers would still be very difficult to program. Yeah. So yeah, just kind of think about. I mean, you guys are so used to. Oh, I can just download an app. Okay, it can update itself. It would do it. It would do all of this stuff over the air. You don't even need a wired connection while you're sleeping, right? So we are totally spoiled. And a lot of times we kind of forget, the invention that were way before us, before we actually get to use computers, that made computers the way they are now. All right, so I'm switching back to the text channel and read what's over there. Wondering what were the other alternatives to the von Neumann architecture at the time. That's basically it. You just basically you have to rewire physically, how the components are connected. That was the only option at the time. And then Bernard said, so you have to create the program, and the computer will only have one program at a time. Yes. Now, technically speaking, your computer still has one program only, which is your operating system. Your operating system is the one that loads, the other programs into memory, and then just kind of in a very controlled manner give control or let those programs execute. So technically speaking, your computer starts with a single program, which is the operating system, which then allows the execution of some of the other programs. But Bernard is correct. These older computers can only have one program at a time. I mean, that whole concept of one program at a time persisted throughout, I think, almost the 80s. So if you look at the early IBM computers, the Apple II computers, they can only run one program at a time. There were no co-processing, there were no multi-processing, there were no multi-process or multi-thread. You know, one program, one thread, one process all the time. Exactly. No multitasking, which I think some of you guys are doing right now, which is okay. Not a problem. All right. So, now that we understand his contribution, what we'll do next is to try to figure out how does a computer maintain data. We are now looking at things from a circuit perspective again. We haven't really looked at things from a circuit perspective for a while. The last time we did that was to figure out, how to create a 3x3 carry look-ahead adder, right? That was the last time we did something with circuits. So what we'll do now is go back and revisit certain types of circuits, but this circuit is very different compared to the circuits that we have seen before. Yet it uses a component that is actually pretty familiar to us. So let's go there. So I'm switching back to my command line somewhere. Where is it? There we go. And start up Logisim. Yes, Logisim is back. And it is back for good as well. In other words, we'll be using Logisim almost every class from here on. Let's start with that, Chris. That's a great idea. Let's go back to PN type transistors and make a NAND to gate first, because I think some people are maybe getting a little nostalgic, right? So we're gonna go back and revisit the NAND gate, right? So, and it's usually not a very bad. It's not a bad idea to kind of revisit these concepts that we have already introduced, at the beginning of the class, because now that you have seen the other stuff, you might actually get an insight that you may not have, back when these concepts were first introduced. So I'm just going to do this relatively quickly. And let's see. And then we want to flip both of these. Let's see, the flow is from top to bottom, so these have to be rotated clockwise, which means we change the facing from east to south. All right, and then we position these things, one over here, and then this one you can go over here, but we wanted to basically do a mirror so that the gate is going to be on the other side, like so. All right. So now we have two other transistors. Both of these are going to be N-type transistors. Okay. Select both, change them from P to N-type, and then these need to, the arrow needs to go up because the source is going to be connected to the ground. So, and the arrow is indicating from source to drain. So we need to change the heading, and this time we need to change this to face north, like so. And I'll put one over here, put the other one down here, and then do a mirror thing so it faces the other side. And now I can draw some wires. Oh wait, I need one output pin to collect the outcome of this calculation. And let's see, we can, yeah, it doesn't look good, but it's gonna work. Alright, so now we can do some wirings. Alright, so the power connects to the source of both of the P-type transistors, and then the ground connects to the N-type transistors in series. And then we have this junction here, and this connects to here, making an actual connection, and this one goes here, making also an actual connection. And now we have to specify, how the input pins connect to the gates of the transistors. So these two is one pair, and then the other pair, oh, some of you are going to frown at what I'm going to do here. This is what I'm doing. I'm used to doing this kind of stuff because I also design circuit boards, and I'm not wealthy enough to pay for something that has an auto router. So a lot of times I actually end up routing the signals myself and do stuff like that. Alright, so we are almost done here. And I need to change both input pins so that they are not going to go for 3-state, which means they can, when you see an X in an input pin, it means it's in high impedance mode, which means it's not a 0 nor a 1, it is an unknown. That is usually not very helpful, so I'm going to turn off 3-state here. Alright, so now we have a working circuit, or at least I think it should be working. So both zeros end up with a 1. That seems to make sense because it's supposed to be a NAND gate, right? So as long as we have at least one input being a 0, it should still be an output of a 1. Yep, okay, so that's good. That is good as well. But when both inputs are 1s, then we have 1 and 1 being a 1, but we negate it as the output, so it should have a 0 as an output in this case. Yep, so that all works. Alright, so that is all working, and then we turn it into a little package like this, okay, and we'll just give it a name. We'll give it a name of NAND, because that's exactly what it does. So this is a NAND gate, and then what do we do with this, right? That's the next question. What are we going to do with this? So the first thing is to give the circuit an actual name. It's not our main circuit anymore. Instead, this is now our NAND circuit. So we're going to change the name of the main circuit to NAND2, being a NAND with 2 inputs. And then we're going to add another circuit, which then becomes our main circuit. So we say add circuit, and this time we'll call it an SR latch, which is the simplest device that has the property of memory at this point. Okay, so we're going to go ahead and take a look at this. Alright, so we're going to have 2 input pins again, and this time we have 2 output pins. So we're going to have 2 input, 2 outputs, and then the other components of this thing would be 2 NAND gates. So we now go to the NAND 2 gate that we just created, get 2 of those. Okay, here's 1, and then Control D is going to duplicate so that we have now 2 of those. And now the question is, how are we going to wire this thing up so that it becomes a memory device? and also how does memory work in this rather simple device here. Alright, so I'm just lining up things so that they just look nicer when it is all done. Alright, so the way we wire this up, okay, the first part is pretty easy. One of the input pins go to one input of each NAND gate, like so. And then the output is really just the outputs of the NAND gates would just go straight to the output pins. Okay, so that part is pretty easy. And then here comes the crazy part. So the crazy part is never before that we have seen a circuit where it has kind of a loop. Okay, I wouldn't call this a loop, but it does have a feedback. Okay, the output of one NAND gate becomes the okay, that's the wrong place to put it. Excuse me. Alright, so it's supposed to go here. So the output of one NAND gate becomes the one of the inputs of the other NAND gate, and it is symmetric like this. Yeah, I'm gonna have to go through the name here, but it's okay. It's not a problem. It just looks kind of ugly. That's all. Alright. So now we have what we called an SR latch. Okay. So we look at this circuit here and go like, it doesn't look like any kind of memory device, but it certainly is kind of interesting. So the question is, how does it work? And also, how can we see these two E things here? Why is it reporting an error? Well, so what we're going to do now is to figure out, how do we analyze a circuit like this, okay? Because this is like nothing that we have seen before. So the question is, how do you analyze a circuit like this, and how do you explain why the outputs are E or error or unknown or cannot be determined? Basically, that's what this means, is that it cannot be determined. So the reason why it cannot be determined is because these are NAND gates, right? So as a NAND gate, no, they should be determined, because if at least one input is a 0, the output should be a 1. So that could be a Logisim thing. Yeah, Logisim is not. Sometimes it just doesn't work. So let me turn it off. Reset simulation and then re-enable it. Same thing. Okay, maybe I made a mistake somewhere in my NAND 2 gate. Alright, so did I make a mistake in the NAND 2 gate? Alright, so that seems to work. That seems to work. And that also works. So I did not make a mistake. Alright, so let's go back to the SR latch. Alright. Okay, so it's complaining it's a E. Alright, so let's see. Okay, so I'm trying to debug the circuit to find out why it's complaining. And it has to do with the second pin is an E. It is not a 0 as what I thought it should be. Alright, so that means I'm not connecting. Oh, that's because this is also a E. Alright. Huh. Okay, so that's why it's not working. That's because it has a feedback, and the feedback of the E makes the transistors not work. Okay, so if this is a 0, it should make a connection. If I replace my NAND 2 switch and my NAND 2 device with an actual NAND 2 gate, it's actually going to work. That's the ironic part. Is in a real circuit, this is not going to be the behavior. Okay, fine. So we're going to do that. I'm going to replace the NAND my homebrew NAND gate with an actual NAND gate. So that way it's gonna work. Because the physical device behaves a little bit differently compared to the logical device in this case. So I'm gonna have to go back to gates, go to NAND. Alright, there we go. And it always gives me this big gigantic gate with way too many inputs. So I'm gonna limit it to only 2. And we also need to change the wiring positions a little bit. Alright, so we need 2 of these. We'll put this one down here. And then put this one up here. And then hook up the wires like so. And now the problem is fixed because it's not a physical device, it is just a logical device in this case. There we go. Alright, so now it works. Alright, so the question is, does it make sense? Okay, does it make sense that when both inputs are zeros that we end up with 2 ones over here? The answer is absolutely. Okay, this is not the problem. Because if this is a NAND gate and at least one input is a 0, that means the output is going to be a 1 already. It doesn't really need to look at this specific input because 1 0 is already enough for a conjunction to end up with a 0. But since this is a negated output of a conjunction, the original 0 as an output of a conjunction now becomes a 1 because we are negating it. It is a NAND. The same thing applies to the second NAND gate because at least one input is a 0 already, which means the output is going to be a 1 regardless of what the other input is going to be. So are we doing okay so far with the analysis of this circuit at this point? And this is all based on, okay, very good. So this is all based on the properties of a NAND gate. So what we'll do next is we are going to change one of the input pins from a 0 to a 1. So let's just say that we are going to flip this one from a 0 to a 1. And now the question is, what is going to happen to this circuit here? So I'm going to let you guys think about it a little bit while I go in and actually make some labels so that we can refer to which input and which NAND gate and which output. So you guys go ahead and think, what if X goes from a 0 to a 1, but Y maintains as a 0? So I'll let you think about it as I just kind of add some names to the components over here. I'm just going to call this N1 and call this one N2. Call this output Q and NQ. There we go. All right. Okay, so let me see what I can do to give you an output here. All right, so Tam already has an okay. Tam and Ian has typed something in the text channel, so the output is going to be 0 1, and I'm gonna guess 0 is Q and 1 is NQ. Is that correct? And then Ian said, isn't this wiring similar to how a room with 2 light switches should work? That I'm not sure. Are you talking about the oh, that's a name for those things. Not really sure, okay, because I'm not very good at what electricians do in terms of those circuits. I don't think it is the same thing because I would imagine you don't want the output of a switch to become the input of another switch. Yeah, I think that's more like an exclusive OR, but it's not having a feedback mechanism like this one does. Okay. Two-way switch, that's it. That's the name, two-way switch. Okay, so you're talking about how a two-way switch works. I'm not sure. Okay, so we can think. I can think about that after class. But at this point, okay, we are looking at this circuit here, and we're trying to figure out what happens when this x becomes a 1. All right. So what we'll do, I can just click here, right? I can change the poking tool and just click here, and Logisim will tell us the answer. But that is not the point, okay? Because the point is, how can we figure this out in our mind, okay, or using a piece of paper? All right, so that's what we'll do, is to try to figure this out without using Logisim, because let's try to figure out the logic of all of that stuff. So I'm going to use some text here and see how well that works. So we want left alignment, okay, and so that I can do some explanation, right? All right, so x becomes 1 first, okay, so that's the change. That's the origin of change. So right after that, what is going to happen? X becomes 1, and then what's going to happen next? Oh, I cannot use a multi-line thingy. There's no way for me to enter multi-line. Okay, fine. I just have to do it this way. All right, so x changes to a 1. So what happens? N1 is going to be changed, because at that point N1, I tried that already, didn't work. So N1 is going to experience both inputs being 1s, right? So now we will say N1 has 2 1s as input. And what is going to happen after that? Yeah, I suppose I do have access to the source code. So x is changed from 0 to 1 first. That's the first event, which immediately changes the input of n1. So n1 has now 2 inputs. Now after a proper propagational delay, I hope this term is still somewhat in your mind after we first introduced this term, right? Because it takes time for N1 to respond to the changes of the input pins. So there's a very slight propagational delay from the time that both inputs of N1 becomes 1s to the change of the output. Can I drag? Oh, right, because my face is in the way. Well, in that case, I am getting rid of my face. Well, not getting rid of my face, but to get rid of the display of my face. Yeah, because there's a very crucial difference between those two sentences. Yeah, that immediately reminds me of Silence of the Lamb. Not good, right? But that's how things connect in my mind. That's why I get distracted a lot. Anyway, so after propagational delay, what is going to happen? N1's output is going to change, right? So N1 changes its output to 0, because as a NAND gate, when both inputs are 1s, then the conjunction becomes a 1, but since the output is negated, that 1 becomes a 0. Okay, so now the question is, all right, so what is the big deal? Well, the big deal is Q becomes 1, because Q is just an output pin. All it does is to report what is the state of the pin. Oh, sorry, 0. So that's the easy one. The more complicated one is, hold on a second here. This is also going to one of the inputs of N2. Fortunately, it's not going to make any changes to N2, but we still have to report it. So now we can say, N2 now has both inputs being 0s. But that's okay. That's okay, because N2 is going to maintain an output of 1. This is awful, because I can only type 1 line at a time, so that's why things are fragmented. It's almost like a ransom letter, except the font is not is still at least consistent. Otherwise, it will look really like a ransom letter where things are just cut and paste into slightly off, unaligned, pieces. There we go. All right. So now we can explain, why this is going to happen. Okay, so I'm actually going to do it, in the in Logic Sim. I'm looking at the time. We still got 10 more minutes, which is enough to finish, this entire discussion that I wanted to do. All right, so let's check, okay? Because we are predicting that Q is going to become 0, right? So Q becomes 0. Very good. And we're going to say that N2 maintains an output of 1, and that it did. Okay, very good. So now what we're going to do, and some of you are going like, no, don't do that. We want that. It's okay. It's okay because you guys, this is all getting recorded, which means you can always get back into the recording and go back to the original text. But I'm gonna have to erase this because now we're moving on to the next stage. I'm getting tired of doing this, so I am going to use another approach to do this. Because I just want to press the enter key and be able to enter text in on the next line. That's all I wanted. So I'm going to use a proper text editor on the side. There we go. All right. So the next question now is, what if I change y from a 0 to a 1? Okay, so I'm going to say y changes to 1. Okay, what's going to happen? Now, obviously, I can just go in here, go to the poking tool, and then change y from a 0 to 1, and Logisim will go through the simulation and tell me what the answer is supposed to be. But Logisim cannot explain the answer to me. All right, so I want an explanation. I want to know why it is like the way it is. Okay, so now I'm going to go through the analysis by hand so that I can understand why the output is going to be what the output is. All right, so the first thing is y changes to 1, and once y changes to 1, N2 has inputs. I'm just going to use this notation here. The first one is going to be a 0, the second one is going to be a 1. So N2 maintains an output of 1, and that's it. Okay, we are done with this analysis. Pretty easy, right? Because N2 is not changing its output, even though y is changed from 0 to 1. So the rest of the circuit are not impacted whatsoever because the output of N1 did not change. All right, so that's the end of this. Cool. All right, so we're gonna use a poking tool here and then change y from a 0 to 1, and as expected, nothing happened. All right, fine. So what we'll do next is we're going to say, what if we change y? Let's see, what did we do? We changed x first from a 0 to a 1, and then we change y from a 0 to a 1. So we're going to change x from a 1 to a 0 now. Okay, so we'll say change x to 0. Okay, and we want to find out what's going to happen in this case when we change x from a 1 to a 0. So we're going to go through the same analysis. Okay, we are going to start at exactly where the change originates and then see how it's going to impact the next component. So x is going to switch from a 1 to a 0, which means one of the input of N1 is going to go from a 1 to a 0, from both inputs being 1s. So that is significant because now we can say the inputs to N1 is 0, 1. But that is significant because N1 is a NAND gate, which means if at least one of its inputs is 0, the output is going to be a 1. So after a propositional delay, so I'm going to use PD to represent propagational delay. The N1, okay, I'm going to use N1 changes its output to 1. All right, are we still good at this point? Why N1 is now changing its output to 1 in response to x going from 1 to 0. All right, all good. All right, so now now we have to continue, to follow that change, because the current change is this node is going from a 0 to a 1. Now obviously it's going to change Q, so Q becomes 1. That's easy to track, okay, because Q is quote unquote a dead end. It is not going to impact anything else. But the other one is going to change is N2, because N2 the inputs to N2 is now 1 1. Oh, so because N2 is a NAND gate, both inputs being ones means its output is going to be a 0. It's going to be a change, right? So now we say after a propagational delay, N2 changes its output to 0. It is a change. So that means NQ is going to change. Okay, that's an easy one. NQ equals a 0. But NQ is just a dead end. Okay, no big deal over there. But this change is also potentially going back to change N1. Now remember, this picture does not represent what we are analyzing. We already know the first input or the top input to N1 is a 0 already. Now the second one is also going to be a 0. So let's note that first. Okay, so the inputs to N1 is now a 0 0. Aha! So this time, whether the inputs of N1 is just one of the input is a 0 or both inputs are zeros, doesn't matter, because if at least one input is a 0, the output is going to be a 1. And the output of N1 is already a 1 as noted here. So that means this is not going to have any further changes. But we probably still want to say after a propagational delay, N1 maintains its output of 0. So there's no change. And because this is not a change, then there's no change propagation to follow anymore. And that becomes the final state of this. Now, before we go there, I am going to take a screenshot first, because it is actually going to be significant after this entire analysis. So I'm taking a screenshot like this, and then sending its output to a program that can display that on the screen. So this way I can go back in time and go like, okay, last time both inputs are ones. This is the outputs are 0 and 1, because this time it's going to change. Alright, so now what do we do? Now we are going to, let's see, we change x to 0. Right, so let's do that first. Okay, so change x to 0, and this is the output, and that is as we expected, because as you can see here, we have NQ being 0. Yes, we have Q being 1. Yes. Okay, excellent. So now we're going to flip, x from a 0 back to a 1 and see what happens. We can do it in Logisim. Well, we got 2 minutes, so I'm just going to try to do it over here. So we change x to 1. So when x is changed to 1, N1 is going to change its input a little bit. So we say the inputs to N1 is now, let's see, 1 0. Because x is only connected to one of the input pins. The other input pin maintains its current state of 0. So after a propagational delay, N1 maintains, okay, it's not changing, it maintains its output of 1. That's because if at least one input of N1 is a 0, the output is going to be a 1. We changed one of them, but we didn't change the other one. So that means, this input of 0, it continues to be a 0, and that's why N1 continues to output a 1, and it was outputting a 1 to begin with, and as a result, this did not end up with a change, and therefore there's nothing to propagate, nothing to analyze. Alright, so now we change x. Okay, so I think that's it, right? So no change at all. So we're going to use Logisim to do exactly the same thing, like that. Then you guys are going to look at this and go like, Tech, what is the significance here? Okay, we got 15 seconds. What is the significance here? Why is this important? And what does this have anything to do with remembering anything, memory, right? So now I'm taking the screenshot from earlier, and you go like, I still don't see anything, right? I mean, both inputs are ones, and one of the outputs is a one, and the other one is a zero. Big deal. Well, wait, hold on a second here. Which one was a one and which one was a zero? They got flipped, right? Because earlier we got q being a 0 and nq being a 1. Now we have q being a 1 and nq being a 0. Now this kind of behavior will never happen when you have a strictly one directional kind of hierarchy of gates, which means you never go backwards. Okay, the output of one thing does not go back and become the input of another thing that is either at the same level or an earlier level. This one, does have a feedback. Okay, this goes all the way back to here, and then this one goes all the way back here. This is what I said about memory or remembering something. Okay, because the proper name of x is actually S for setting, so I'm just going to use the entire word set here, and then Y, the name for Y is R, which is reset. And the way it works is when it is a 0, it's either sets, which means changing to a 1, or reset Q. So when set is a 1, it is supposed to change Q to a 1. When reset, excuse me, let me say that one more time. When set is a 0, it is supposed to change Q to a 1. When reset is a 0, it's supposed to change Q to a 0. That and when both are ones, it is supposed to, now this is the most important part of this lecture. When both inputs are ones, it is supposed to remember or maintain the current output state of the SR latch. That is the memory part of this very simple memory device. I don't think so. What you are giving me in the picture is there's a name for these things. These things here are is to make sure that you don't get electrocuted in the bathroom, right? So if you plug your hair dryer to one of these things, and let's say you're in the tub, okay, and you're running your hair dryer when you're in the tub filled with water, and then you accidentally drop your hair dryer into the water, which normally would not be a very good thing to do because you're going to get electrocuted. So this is there's a name in the fault is a part of the name of this kind of socket, but I cannot remember what it is. Ground fault interrupter. Thank you. That's it. Okay, is a ground fault interrupter, and the way it works is it's actually a mechanical thing in the inside. Somebody actually explained it to me. It has to do with it finds when it detects. Oh, that's right. Okay, so it's very sensitive to where the live wire returns the current. Okay, because there are two ways for the current of the live wire, which is the one, is it the white one or the black one? I think it's the black one. So the black wire is the live wire, and you can see it as the source of current. So it has two ways to return to the generator. One is through the neutral wire, which is the white one. The second one is to go through the ground, which is literally the ground, okay, which is literally earth, okay, and that's another path for electricity to kind of complete the circuit to go back to the generator. That's way far from us. Or just the transformer, which in this case would be very close to us. So when it finds out that a very small amount of current is not returning using the neutral wire, then it is going to it's going to pop the switch. Okay, it's going to disconnect the switch because there's a ground fault. This is called a ground fault because there's a connectivity between the live wire going through some kind of a load, in this case U, to ground, and that's not a good thing. So this type of socket can detect a very small current going through a load into the ground as a return, back to the, instead of using the neutral wire. And when it detects this really small current, it pops the switch. It disconnects the switch, and therefore saving you from being electrocuted by yourself. Yep, GFCI. Yep, ground fault something interrupter. Circuit. I would say, I will bet you the C is a circuit. Ground fault circuit interrupter. So yes, so after explaining all that stuff, it does not have anything to do with an SR latch. But the SR latch is the most fundamental device for remembering things. So next class, on next Tuesday, we're going to be constructing D flip-flops, all kinds of D flip-flops. No, it has nothing to do with those things that you wear. Yes, I know how you guys think. It's like flip-flops. Oh, okay. I know what a flip-flop is. No, has nothing to do with that sort of flip-flop. So the D flip-flops are more complicated memory devices. So at some point we're going to go to a device where, yeah, so just there are ways to tell this device here to remember a bit, okay, a single binary digit. So if we hook up 8 of these things, in a certain way, then we'll be able to remember 8 bits, which is a byte, okay? So that would be the objective of next Tuesday, is to go through that module, the module that we are on, which is, we are not on it, but I will show you where to find it so that you can read it over the weekend. Oh, let's see, where is it? Nope, too far back. There we go. D flip-flop and other basic memory devices. That is where we are supposed to be reading over the weekend, and also doing the programming for the floating point number thing. So 0298 is the module number, and what we have done so far today is to explain the SR latch, and this is a text description of the same circuit. And I believe I even use exactly the same name, other than S and R, which later on I switched to. But otherwise, N1, N2 being the logic, being the NAND gate, Q and NQ being the outputs, same thing. So you can basically figure out how to interpret the text description of the circuit. But the analysis of the circuit is basically what I just did earlier today. And this is the smallest memory device. This is the elemental device that we use to make larger and more easily utilized memory devices. And that is the first step. Okay, once we understand how to make these things, D flip-flops, and then how to make it like 8-bit wide, then we have registers. And once we have registers, then we have the components, all the basic components that we need to specify how a processor is designed. So that's kind of where we're heading. So the next week we're going to be using some of the time next week to finish up this module, which is module 0298. And then after that we'll start to talk about some of the other components that we find in the processor. So we're getting pretty close to explain, the components inside the processor and how all those components interact with each other. So we're getting there for those of you who are just itching to write programs in assembly language. So we are getting there. All right, so are there any questions before I get out of the voice, the screen share and the live stream? And there are, so the lab is, let me go assign the lab first. Okay, I almost forgot to do that. Or maybe I did. I will double check. I think I have not done that yet. But it's a very similar homework assignment compared to the negative exponent. I have not released it, but I'm going to release it now. There's no passcode to it. So what you need to do is to turn in a program. So let's see. So I'm going to make this due in a week as well. So you have until today is the 3rd. So you have until the 10th at 5:30 p.m. to turn it in. If I were you, I am going to finish both of these programs over the weekend. Because once you finish one, the other one is very, very easy to finish as well. So I'll just go ahead and use the weekend to finish both of them. Um, so this way I can use next week to focus on the new concepts. All right, and let's see. Yes, you. Yep, I just assigned 1 week from today for to answer Chris's question. So it's not exactly 1 week. It's 1 week minus the 1 hour and a half for the lecture. Um, and then the next question is coming from Kushal. When x and y both are ones, which gate logicism calculates first? So it's not about that. Okay, that's a very good question. It's about the change. So this has to do with change propagation or change tracking more so than how what happens when both inputs are ones. So the transition to 1 1 as both inputs into the circuit here is we're only changing one pin at a time. Okay, so I'm going to address the question of what happens when you change both pins from 0 0 to 1 1 or something like that, but that's not the point at this point. Okay, so right now I'm just going to say the most important part is you're only changing one input pin at a time. So the question is, what happens when this R pin changes from 0 to 1? Okay, so when this changes from 0 to 1, then you have one input of 1 to N2, but the other input to N2 maintains, is still a 0, which means N2 will maintain its own output as 1, and that changes the change propagation because N2 is not going to change its output. So that is why when I change the R pin from a 0 to a 1, nothing changes. Okay, and this is what we call a steady state, which means this by itself is not going to change. So you can analyze this, but since it has no changes, it's a steady state. So to analyze a steady state, there's no start and no finish because N1 and N2 are responding to their inputs simultaneously. So you kind of have to track both at the same time. They are in parallel. So while N1 is seeing both inputs as ones, it is naturally outputting a 0. And at the same time, N2 is looking at its inputs. One is a 1, the other one is a 0, which means N2 is supposed to output a 1. And this 1 here becomes a part of N1, which it was already, right? Because that was the inputs to N1. And this output of N1, which is 0, is also continuing to be a 0 to N2. So you can kind of look at it that way, and this ends the analysis because neither N1 nor N2 is going to experience any changes to their inputs respectively, and as a result their output will not change either, and that can basically stop the analysis. So I hope this answers Kushal's question. But the point of the lecture was not to do a steady state analysis, which is what I just did, but only to track what is changed and how that change is going to propagate through the other components in the circuit. So good question, except I did not address this specific question in class because I was more concerned about how the changes are going to impact the components in a more or less sequential manner. All right, so I think that's it, right? So you got your new homework assignment, the positive exponent assignment, and you still have the negative exponent component. One is due, the negative one is due on Tuesday. The positive one is due on Thursday. Now, for some of you, because you say, but I can do both at the same time, so can I turn in the same program for both assignments? The answer is yes, you can turn in the same program for both. But what I'll do is I'm only going to test negative exponent cases for the negative exponent assignment, and I'm only going to test the positive exponent for the positive exponent component assignment. But if your code works for both anyway, hey, it doesn't make a difference, whether you turn in the same program for both assignments or not. So, for those of you who get everything done before Tuesday, you can just turn in the same program for both assignments. All right, so I think I got everything done today, and I am going to get out of screen share, but I'll still be around, to answer questions. So if you are working on the programs and you have a question, you go ahead and use the text channel to ask me, or you can also request a voice chat if that is what you want. But I'll be around until 9:50. All right. So have a nice weekend. If I don't quote unquote see you, and then I'll see you all on next Tuesday.